Hey guys, this recording is for 3.1. Okay, so I'm going to, technically I should start with example 2 because most of the classes already got example 1 finished, okay? Except that in third period, we are in the middle of example 1 for the second formula with this, which is called the alternative formula. We were down to here. We factored out by grouping, so here we are as factors. So the next step, I know 2 of my classes are done with this process, so just kind of listen just again, okay? And then you will do example 2 next. And so here we go. So these 2 things right here are in common. So by factoring by grouping, you, again, factor that common term out. So what you are left with was really an x plus a and then plus 3, okay? All over x minus a. Well, these 2 things are going to cancel. So from here, by substitution, okay, by substitution, you should know that every time, so if I say, well, you know what, x approaches 2, what do you do here? You put in 2, right, every time you see an x. Well, I don't have a 2, I just made that up. So what you do is every time you see an x, you put in an a, okay? So here you have a, and then you drop this down because this is what you're left with. The a plus a is 2a plus 3. This right here, class, is the derivative at a, okay? The derivative at a. Because remember, a was a point that we were supposed to know. So these 2 things should always be very similar to one another. Whether you do the derivative of x first, then plug in a, or if you know the point from the beginning, you can use the derivative of a point and work that out, okay? So it doesn't matter how you do it, whether you use the formal definition or the alternative definition, which is the derivative at a point, your answer should be the same. Now, example 2 says, apply the formal definition to our function f of x equals sine of x, okay? So we are going to write the formal definition first. F prime of x, that means the derivative of function f, is the limit as h approaches 0 of f of x plus h minus f of x all over h. This is just the definition. I'm just writing it down for you. Now let's work it out together. So by definition, the limit as h approaches 0 of f of x, that means I now have sine of x plus h, okay, minus sine of x all over h. And I hope that you remember your sum and difference formula. So here we go, sine of x cosine of h, okay? Then I'm going to add cosine of x sine of h, and then just drop the sine of x back all over h, okay? Then continue, limits as h approaches 0. I'm going to try to factor this out because right now if I plug in h, that's not going to work very well. But I do see that this right here has something in common, so I'm going to try to put those 2 together as one group, okay? Cosine of h minus sine of x. I'm going to put that together as one group, and then I'm just going to drop down everything else that's not in that group. So now all over h, which is limits as h approaches 0. Now I'm going to take out the sine of x, okay? I'm left with cosine of h minus 1 all over h, okay? But here's what I'm also going to do. Based on our limit properties, I'm allowed to add limit as h approaches 0 of cosine of x, okay, times limit as h approaches 0 sine of h. What am I doing here? I'm just using the limit properties and break these into pieces, okay? So keep in mind that these are all still all over h, okay? So this whole thing is all over h, but I don't want to write all over h like that, right? I just want to write 1 here, okay? So technically, you know what, let me just write that next step, all over h here. And this is technically, both of these are still all over h. Okay, so you know what? Let me just write that. Let me just insert that step in the middle so that way you're not confused. So since I broke this up, technically this is really just this. Okay, all over h. Okay, well, next I'm going to write limits as h approaches 0. I'm going to write sine of x all over 1. Okay, times cosine of h minus 1 all over h that way. Then I will break this up, limits at h approaches 0. And then same thing with this, I can break it up as only one of it, right? Put sine of h over h times cosine of x over 1. Okay, so you can always do that using our properties of limits. So what's happening? As h approaches 0, remember, this is one of the properties you were supposed to know as h approaches 0. Okay, that property is what? As h approaches 0, that is 0. Okay, and you're supposed to know this. This is what? This one over here is 1. Okay, so, well, I have 0 over here. I still have the limit as h approaches 0 of sine of x, right? And over here, I now have 1 times the limit as h approaches 0 of cosine of x. Well, what's going on here is as h approaches, so what's going on is, well, what's going on? I don't know when h is approaching 0, right? 0 times anything is 0. Okay, so over here, this whole thing is going to be 0, right? This whole thing is going to be 0, okay? Because I don't care what this is, right? H approaches 0, it's just not even in this equation. So whatever sine is, okay? So sine times 0 is 0. Over here, well, guess what? This limits right here. The limits as h approaches 0, h is not even in this equation. So cosine of the limit of h approaches 0, cosine of x is just cosine of x, okay? So that right here is just cosine of x. So guess what? The derivative becomes just cosine of x, okay? So what do we take from this? The derivative of sine is cosine of x, okay? So the derivative of sine is cosine of x. So keep that in mind. Now, do you have to do this proof over again? No. From now on, if I ask you, what's the derivative of sine of x? You could just write the answer. It's cosine of x. And let's go and graph that out really quickly, okay? I'm going to use our Desmos. Here we go. I'm going to type in sine of x and cosine of x, and then you can tell me what's going on, okay? So we are going to use function sine of x. That will give you this beautiful piece. Next function, let's do cosine of x, okay? Okay, so as you can see, the graphs are definitely different, okay? There's no doubt about that. So how are the derivatives, okay? How are the derivatives the same? Remember, the derivative isn't looking for, the derivative is looking for like, hey, what's happening at a particular point, right? So the derivative is talk about, hey, if I move this, okay, if I move this along x, okay, what's going to happen? Okay, so what if I do a little animation for us, okay? So keep in mind the red one is your sine, and then the orange one is your, the colors are changed. The orange one is your cosine. So remember, the derivative is a slope at a point, okay? So, and sine keeps on going forever. So what if I were to find a tangent at every single point, okay? Every single point on the sine curve. So follow that really quickly. And so guess what's happening? Every single point on the sine curve, as we find the slope, guess what's happening? The height makes the value that we can use to graph, cosine, okay? And again, the height, okay, or the tangent of sine, okay? So the height or the tangent of sine gives us values that can be used to plot your cosine. That's exactly what's happening. So the derivative of sine is cosine, okay? So that's what this animation is supposed to be, okay? So the tangent at every single point on the sine curve gives us the perfect point to plot out cosine, okay? So that's what's happening there. So as that algebraically, and hopefully the graphing helps a little bit, okay? Oh man, okay, so let's go do this one right here. Example 3, find the derivative of f of x equals 1 over x at x equals 3. So as you can see, this one you know, okay? You know a point, x equals to 3. So I'm not going to use the formal definition. I'm going to use the derivative at a point definition. So first I would like to do is I want to find out what f of 3 is. Okay, so f of 3, let's find out what that is. Let's plug it in. 1 over 3, it's just going to be 1/3. So 3 comma 1/3. It's my point. Okay, so formula says f prime of your point, whatever this point is, a, is the limit as x approaches a. In this case, your a is 3, okay? X approaches 3. F of x minus f of 3, because that's f of a, all over x minus 3, okay? So by definition, limits as x approaches 3, which is going to be f of x, which is 1 over x, minus f of 3. I found f of 3 already from here, so I'm just plug in 1/3 minus 1/3 all over x minus 3. I'm now going to find the common denominator for the top. So that's going to be 3x. That means I'm going to multiply this side by 3 and this side by x. Okay, so that's going to be 3 minus x. Okay, divided by 3x. Okay, so this is one of them. So now I'm going to do division this way. And I think some of you will be able to see why I'm writing it that way. Okay, because now if I were to go and multiply by its reciprocal, guess what happens? I'm going to now rewrite negative x plus 3 this way, all over 3x. Divide is now multiplication of its reciprocal of x minus 3. From here, I will factor out the negative, right? So now it's x minus 3 over 3x times 1 over x minus 3. This will help me reduce this right here. So I now have negative 1 over 3x. So the limits, that's x approaches 3 of a negative 1 over 3x. Okay, so as you can see, I'm kind of the end. Now I just have to do is plug in your a or your x really. So at x approaches 3, by substitution, my derivative at this location, it's 3 times 3, which is going to be 1 over negative 1 over 9. Okay, so this is the derivative at a point. In this case, the point is when x is 3. So that is the final answer for the derivative when x is 3. Okay, so this is just going to be the end of this video.